Think for a second about the incredible technology that surrounds us. From the smartphone in your pocket to the satellites orbiting Earth. What if I told you there's a fascinating material poised to make many of these things even better? And researchers have just found a much simpler and safer way to create it.
That's right. Today, we're taking a deep dive into the world of MXenes, pronounced MXenes. They're a really exciting class of two-dimensional nanomaterials.
MXenes, okay.
You're probably familiar with graphene, right? That Nobel Prize-winning single layer of carbon that caused such a sensation a while back.
Yeah, absolutely.
Well, MXenes are kind of in the same ballpark, incredibly thin materials where stripping away certain layers reveals these remarkable new properties.
Okay, so just to get a clearer picture, when we say 2D materials, we're talking about materials that are essentially just a few atoms thick, right?
Exactly.
And MXenes, you mentioned they're mainly titanium and carbon.
Precisely. Think of it like taking a block of material, like a layered cake, and peeling off layer after layer until you're left with something incredibly thin, almost like a sheet of paper, but, on an atomic scale. Now, MXenes are special because they're typically made of layers of a transition metal carbide or nitride, like titanium carbide.
Okay.
And these layers are sort of sandwiched together with other elements. In their raw form, which we call max phases, one of these in-between layers is often aluminum. And the traditional way to get to the actual MXene, the useful 2D material, was to essentially dissolve away that aluminum layer.
Dissolve it away.
Yeah.
Okay,
Right.
and that's where the old method got a bit hairy, as I understand it. It involved some pretty nasty chemicals, didn't it?
Exactly. For years, the standard way to produce MXenes relied on hydrofluoric acid, HF.
Ah, HF.
Right.
Not friendly stuff.
No, not at all. While HF is very effective at selectively eating away those aluminum layers to reveal the 2D MXene structure, it's incredibly dangerous. We're talking highly toxic, highly corrosive, requires specialized labs, really stringent safety measures, and then you have the hazardous waste disposal issue.
Right.
So, yeah, a fantastic material held back by a less than ideal, frankly, dangerous production process.
Right, so a classic case of great potential, but a significant practical hurdle, a bottleneck.
Major bottleneck.
But the exciting news, and this is why we're diving in today, is that researchers at TU Wien, that's Vienna University of Technology, along with collaborators at CEST and AC2T, they've come up with a brand new method. And it sounds like a real breakthrough for creating MXenes.
It truly is. I'd call it a game changer. They've developed an electricity-based approach to synthesize MX, completely eliminating the need for hydrofluoric acid.
Wow, okay.
This has massive implications across the board.
Okay, so instead of bathing these max phase materials, which are like the unrefined version containing the aluminum in that nasty acid, they're using electricity. How does that actually work?
That's the core of it, yeah. They use an electrochemical technique, basically by carefully applying a specific electrical voltage to the max phase material, which is sitting in a special solution, they generate an electric current.
Okay.
And this current, it selectively targets the chemical bonds holding those aluminum layers in place.
Ah, so it's targeted.
Very targeted. Think of it like using a very precise electrical current as a tiny, almost invisible tool to gently nudge away only the aluminum atoms, leaving the desired titanium carbide layers completely intact.
What's fascinating here is this idea of such precise control. It's not just like a jolt of electricity. It's about fine-tuning the voltage to only remove the aluminum. That's pretty ingenious.
It is. And what's even more clever, I think, is their use of pulsed currents.
Pulse currents.
Yeah, short bursts of electricity rather than a continuous flow. They discovered that these pulses actually make the process much more efficient.
How so?
Well, these pulses cause tiny hydrogen bubbles to form on the surface of the max phase.
Hydrogen bubbles, okay.
Yeah. And these little bubbles act like miniature cleaning crews. They constantly sort of refresh the surface, keep it clean, and make it more reactive. This allows the electrical etching, as they call it, to continue for longer and produce more MXene with really consistent quality.
So these tiny hydrogen bubbles are like microscopic scrubbers, constantly prepping the surface for the electrical current to do its work more effectively. That's a really neat trick.
It is, isn't it? A very clever piece of electrochemistry.
And the end result. The MXenes produced this way, are they actually as good as the ones made with the dangerous acid? Or is there a trade-off?
That's the crucial question, right?
Probably.
And the answer is yes, they are just as good, if not better in some ways. They rigorously tested these electrochemically produced MXenes, they even call them EC MXenes, for electrochemically synthesized.
EC MXenes.
They used really advanced tools, things like atomic force microscopy and electron microscopy, to look really closely at their structure, their layers, and various types of spectroscopy to analyze their composition and purity. The findings were clear. The MXenes were at least as good as the traditional ones, same layered structure, high purity, and they performed just as well in functional tests.
That's fantastic. So no compromise on quality, but a huge improvement in safety and presumably environmental impact.
Exactly. Huge improvement.
Which brings us back to the why this matters part. We sort of touched on some of the incredible potential applications of MXenes at the beginning. Remind us why these materials are so exciting in the first place.
Certainly. MXenes have shown immense promise in a whole host of fields. It's really down to their unique combination of properties. Their excellent electrical conductivity and that layered structure make them ideal for electromagnetic shielding.
Shielding, like protecting electronics.
Exactly. Imagine devices that are completely protected from electronic interference. That could mean more reliable medical equipment or maybe more secure communication channels. Big implications there. In energy storage, MXenes could potentially revolutionize batteries and supercapacitors.
Ah, better batteries. Everyone wants those.
Absolutely. Potentially leading to electric vehicles that charge in minutes instead of hours, or devices that last much, much longer on a single charge. They're also being explored for advanced sensors, really sensitive ones that could detect even tiny trace amounts of gases or other substances.
Okay, lots of potential there. And then there's the application that really caught my attention, their potential as exceptional solid lubricants, especially in really extreme conditions.
Yes, this is a particularly compelling area. Because of their atomically thin layered structure, MXenes can slide past each other with very, very little friction. Almost like a deck of cards, but on a nanoscale.
Super slippery, basically.
Extremely slippery, yes. This makes them perfect for lubrication in environments where traditional liquid lubricants just won't work. Think about the vacuum of space where liquids would just, poof, evaporate.
Right, or extreme temperatures.
Or in extremely high temperature or high pressure industrial machinery. Imagine spacecraft components, like moving parts on satellites or rovers, that can operate flawlessly for years without needing any lubrication maintenance. Or industrial processes that become far more energy efficient simply due to reduced friction.
Okay, so we have this amazing material, MXenes now, with all these potential game-changing uses. But the hazardous production method using HF was a major roadblock. Now that this new, safer method exists, what kind of opportunities does that unlock? How does it change things for, say, wider industrial use?
It essentially removes a huge barrier to entry for many industries. The safety concerns were significant. The high costs associated with building and maintaining facilities to handle hydrofluoric acid safely, the environmental impact of disposing of that hazardous waste. These were all major deterrents.
Makes sense.
This new electrochemical method is much cleaner. It's inherently safer for the researchers and production teams, and it's far more environmentally friendly, less hazardous waste to deal with. And crucially, by eliminating the need for HF and all the associated infrastructure, it also opens the door for potentially more scalable and cost-effective production of MXenes.
That makes perfect sense. If companies don't need to invest in highly specialized and expensive safety equipment and protocols for dangerous chemicals, it stands to reason that many more might be willing to explore actually using MXenes in their products, in their manufacturing.
Absolutely. It lowers the activation energy, so to speak, for adopting this technology. And it's not just about massive industrial applications, potentially. Pierluigi Bellato, one of the lead researchers at TU Wien on this project.
One of the scientists.
Yes. He even spoke about a future where MXene synthesis could become, in his words, extremely simple. He even aspirationally mentioned it being possible in any kitchen one day.
In any kitchen. Wow, that's ambitious.
Well, it might be an ambitious long-term vision, sure, but I think it really highlights the transformative potential they see in this research, making these advanced high-performance materials far more accessible, not just to big industry, but potentially to a much broader range of users and applications down the line.
In any kitchen, that's a fascinating thought. From highly specialized labs needing extreme precautions, hazmat suits maybe, to something potentially as straightforward as, well, maybe not making coffee, but much, much simpler. It really underscores the significance of this breakthrough.
It truly does. It suggests a future where these materials with these incredible properties, conductivity, lubrication, energy storage, could become much more commonplace, impacting various sectors and potentially improving our daily lives in ways we can't even fully envision yet.
So let's try and bring it all together then. We've explored MXenes, these incredibly promising 2D nanomaterials, applications ranging from next-gen batteries and electronic shielding to lubricants that can literally work in the vacuum of space. The major challenge, the bottleneck, has always been the dangerous hydrofluoric acid needed for their production.
The HF problem, yeah.
But now, thanks to these researchers at TU Wien and their collaborators, we have a new, much safer electricity-based method, an electrochemical method.
Using pulsed currents and those helpful little hydrogen bubbles.
Right. And it produces MXenes, MXenes of comparable, maybe even superior quality. This could really pave the way for widespread industrial adoption and finally unlock their full potential.
Precisely. I think this innovation tackles that critical bottleneck head-on. It makes the future of MXene technology look significantly brighter, definitely safer, and much more sustainable.
It certainly does. It really makes you think, doesn't it, about the implications of just easily accessible, high-performance, solid lubricants, for instance. Imagine more durable machinery everywhere, reduced energy consumption across the board. And that's just scratching the surface with one application. What other possibilities might this unlock for you, the listener, as materials science continues to advance in this exciting way? It's definitely something to ponder.
Absolutely. And for those listeners who are keen to dive into the real technical details of this specific research.
Yeah, the source material.
The findings were published quite recently in the journal Small. If you want to look it up, the DOI is 10.100 says SMLL Tot 202500807. It's well worth a read if you want to explore the science behind this breakthrough in more depth.